In this video in our Chemistry of the P-block series, we're going to be looking at group 7 of the periodic table and focusing specifically on the oxidizing powers of the elements in that particular group. Before we jump into this though, I thought it might be useful for us first of all to remind ourselves of what we already know from GCSE and our AS work on group 7 elements. So hopefully we remember that group 7 of the periodic table lies towards the right-hand side of the P block, involving fluorine, chlorine, bromine, iodine, and astatine. If we remember our electron configuration work, then we will recall that all of these elements will have their valence electrons in S2, P1, 2, 3, 4, 5. So fluorine here would be 2s2, 2p5. Chlorine 3s2, 3p5, bromine 4s2, 4p5, iodine 5s2, 5p5, and astatine 6s2, 6p5. Okay, if we look a little bit more closely at this group then, and remind ourselves of some of their physical properties, these are very colourful elements, and you may recall that fluorine at the top of the group is a very pale yellow coloration. Diatomic molecule F2, and at room temperature fluorine is a pale yellow gas. If we move down to chlorine, again we see coloration. This time however it's a pale green colour, and again chlorine is a diatomic molecule, two chlorine atoms bonded together, covalent bond, and again it's a gas at room temperature. Moving down the group again, this time we come to bromine, and bromine is quite an intense orangey brown coloration. Another diatomic molecule, Br2. However, this time we have enough electrons in bromine for the van der Waals forces between neighboring bromine molecules to be strong enough to allow bromine to be a liquid, only just, but it is a liquid at room temperature. Fun fact, bromine and mercury are the only two elements in the whole of the periodic table which are liquids at room temperature. Once we go down to iodine, it's a little bit difficult to pinpoint iodine's color. It's a grayish purple sort of solid at room temperature. Again, enough electrons here now for the van der Waals forces between the neighboring iodine molecules not to allow iodine to be a liquid at all, but allow it to be a solid at room temperature. Iodine, if you dissolve it in water, it's a kind of a reddish brown solution. If it's dissolved in non-polar solvents, it tends to be more of a purple solution. So it's a little bit awkward to pinpoint iodine's color. Astatine at the very bottom of the group, extremely rare, highly radioactive, so we don't really come across it or deal with it much at all. However, it's a diatomic molecule. It's going to be dark in color, almost black, and again, it's a solid. Okay, if we start thinking about their reactivities then and remind ourselves of what we know about their reactivity, as we descend the group, the reactivities of these elements, if you remember, decreases. Fluorine at the top of the group here is the most electronegative of all of these elements. It is extremely good at pulling electrons towards itself, and it will become a fluoride ion, which is very, very stable. Chlorine is, again, fairly electronegative, not as electronegative as fluorine, but chlorine is still quite a reactive element, and again it will attempt to draw in a pair of electrons to a Cl2 molecule and form chloride ions. As we descend the group though, the ability to do this diminishes. Bromide ions form from bromine, not so readily. Iodine becomes less electronegative again, and now it's struggling to pull in a pair of electrons. and form an iodide ion. And we never talk about astatine reacting, but I suppose if it did react, it would do it in a similar way, although very unreactive, because it's not electronegative at all. So electronegativity decreases down the group, and that is related to their reactivity decreasing as well. Another thing to bear in mind before we move ahead is to recall that once these ions, negative ions, halide ions, have formed, they will all tend to be colorless or white crystalline solids. They have lost their color. More often than not white solids. You do get the odd exception. For instance, if lead and iodide ions, lead iodide is a very vivid yellow color, but that's an exception. Most of these, when they join up with the counter ion, a positive ion, they will form white crystalline solids. They lose the color that they had as they're in their elemental states. And likewise, if those solids are dissolved in water, they form colorless solutions. Okay, I think that's all you should hopefully need to know. One last thing before we move ahead with A2 work is you might be worth you reminding yourself of this mnemonic which was taught to you in year 12. In year 12 we talked a little bit about redox reactions, and we used this mnemonic to help you remember that oxidation is the loss of electrons, if you recall, losing electrons, and reduction is the gain of electrons. That will be useful if you can remember that in this work. Oil rig, oxidation, loss of electrons, you're being reduced, you're gaining electrons. Okay. Let's crack on then with our year 13 work that we need to know. Right, so oxidizing powers. One way of assigning oxidation strength to an element is to use what's referred to as standard electrode potential values. They have this E symbol. Now, you've not come across these yet, but you will study them in quite a lot of depth when we cover redox in year 13. However, at this stage, all you need to appreciate is the more positive the value, the stronger the oxidizing agent tends to be. So if we take a look at the top of the group here and look at fluorine, fluorine gas accepting an electron to become fluoride ions gives us quite a large electrode potential value. Now, I know 2.87 doesn't seem a very big number, but in the world of electrode potential values, that is quite a large value. Quite a large positive value. That tells us that fluorine is very good at pulling in electrons. It has a high affinity for electrons. It's highly electronegative, and it wants to form fluoride ions. If we compare that with chlorine, not quite so good. In fact, nowhere near as good. 1.36 volts is a significant drop, telling us that there's a big difference in reactivity between fluorine and chlorine. Move down again, another drop to bromine, and again another drop to iodine. So this should correlate with what we just talked about in terms of electronegativity decreasing and reactivity decreasing. So this value basically tells us that fluorine is the strongest oxidizing agent in this group. This value tells us that iodine is the weakest oxidizing agent in this group. Remember, to be an oxidizing agent, you've got to be taking electrons away from other species. To oxidize them, they have to have their electrons have been lost. And so fluorine is brilliant at stealing electrons. It's a proper electron thief, and it's a very potent oxidizing agent. Iodine is a rubbish electron thief, and as a result, it's a very poor oxidizing agent, and this value tells us that. However, if you notice, these are equilibria values, symbols, and so these reactions can be reversed. And so if we think about it going in the opposite direction, essentially this number tells us that this equilibrium lies far, far to the right-hand side. Fluoride ions are extremely stable, fluorine molecules are not stable at all, and so fluorine wants this equilibrium will lie towards the right hand side, forming F minus. On the other hand, towards the bottom of the group, the equilibrium is more to the left hand side. Iodide ions are relatively happy to give up their electrons to form iodine. And so if we think about it in another way, fluoride ions are hopeless reducing agents. To reduce something, you've got to provide that species with electrons. Remember, reduction is gain of electrons. And so fluoride ions are hopeless reducing agents. They are not going to give up electrons and give them away to anything else. On the other hand, iodide ions are not too bad at reducing other species. They are relatively happy to give up their electrons and pass them on to other species, thereby reducing those other species. And so of the 4 halide ions we have here, iodide ions would be the best reducing agents. Notice that we've left out astatine because, as I said earlier, it's radioactive and it's very, very rare, and we never really count it in terms of chemical reactions. So, to summarize then, as the value for fluorine is the most positive, it readily gains electrons to form fluoride ions. This allows it shows that it is difficult to oxidize those fluoride ions. Remember, if we're coming back towards the left-hand side, that would be the fluoride being oxidized itself to fluorine. That ain't going to happen. On the bottom of the group, as the value for iodine is the least positive, it gains electrons less readily than bromine or chlorine or fluorine. This also shows that it's easier to oxidize the iodide ions back to iodine than it is to oxidize bromide or chloride or certainly fluoride ions back to their respective halogens. Okay, so all that stuff should be relatively familiar. The only new thing here are these electrode potential values, but don't get stressed by these. You will come across them when you do your redox work in year 13, but suffice to say, a bigger number means that this equilibrium will lie towards the right-hand side, and that tells us that that species is very powerful oxidizing agent. Smaller number, equilibrium lies more to the left-hand side, iodine is a very poor oxidizing agent. Right, so what you're more familiar with perhaps from GCSE and I think AS level are the displacement reactions of these halogen halide reactions. So if we take, for instance, some chlorine water and pour it into a flask that we have here, some chlorine water going in there, Cl2 aqueous, and then pouring some petrol on top of this. Not necessary at all for the reaction, but it helps to see things at the end. The next reagent I'm pouring in is sodium bromide. Notice how it's colorless as it goes in, but as soon as it hits the chlorine water, we get this yellow coloration. I then take that and shake it up. By shaking it up, that yellow coloration concentrates itself in the petrol layer that I put in there. And of course, that orange color tells us that we've formed some bromine here. And this is a displacement reaction. Obviously, there would be a counter ion here, something like sodium or potassium. And that bromide has lost an electron. That electron has been taken away by chlorine. Remember, chlorine is a stronger oxidizing agent, higher electrode potential value, and therefore it's very easy for it to take that electron away from bromine and form Br2. And also, the Cl2 will become Cl-. So we have effectively a reduction process going on here from chlorine to chloride. Remember, oxidizing agents like chlorine get reduced themselves. And we have an oxidation process here from bromide to bromine. So this occurs because chlorine is a stronger oxidizing agent than bromine, more positive electrode potential value as we saw earlier. This means that chlorine is able to oxidize bromide ions to form bromine molecules. We can do the same kind of thing if we took chlorine and iodide ions, for instance. So in this flask, again, I'm pouring in some chlorine water, then some petrol, not necessary, but it helps at the end. Then we've got some sodium iodide going in, colorless as it goes in, but as soon as it combines with the chlorine water, we see this reddish-brown color. Shake that up, and the reddish-brown color, some of it at least, goes into the petrol. It gives you that beautiful purple coloration, and that's indicative of iodine having been formed. As I mentioned earlier, iodine is a tricky molecule, tricky element in order to assign a color for it. Grayish purple as a solid. You can see this reddish brown solution in water. You can see the purple solution in petrol. So it's a tricky one to assign a color to precisely. But I've put it here as the reddish brown color because in there it's dissolved in water. So here again we have another oxidation process going on. This is a redox reaction. Iodide ions being oxidized to iodine. The electron, the negative charge here, been ripped off it by chlorine, which is the stronger oxidizing agent, and so it's able to take that electron away with ease. The chlorine is being reduced to chloride ions. The iodide is being oxidized to iodine. So this occurs because chlorine is a stronger oxidizing agent than iodide. Again, the electrode potential values that we saw earlier confirm that to us. This means that chlorine is able to oxidize iodide to form iodine. So, oxidation strength of group 7 then. So to summarize, as we go down this group, we know already that reactivity decreases rather. Fluorine's the most reactive at the top, the strongest oxidizing agent. As we come down, oxidation power diminishes. If we look on the other side though, reminding ourselves that these are all reversible processes, if we leave astatine out of the discussion, iodide ions are the strongest reducing agents here. They are the ones that are most able to give up their negative charge, to give up their electrons and form iodine again, and they are the best reducing agents. So fluorine, strongest oxidizing agent, iodide, strongest reducing agent. So fill in your booklet on this particular topic and have a go at some of the past paper questions. There are not that many of these questions at A2 because we're sort of touching on AS/GCSE knowledge here, but there are some, and I've included them in the back of the booklet for you to have a go at.